All right, I sound like right here? How's this? Good so far? Okay, so thank you very much. My name is Matt Marcus. I'm a PhD candidate at the University of Maryland, College Park in the Aerospace Engineering Department. And I want to thank SBAG for providing the travel funding, allowing me to come to this meeting to talk about my work on a number of small bodies concept studies I've done during my time in grad school. So I've been at the University of Maryland for quite a while now. I got my bachelor's degree there and then my master's degree in 2015 on low Earth orbit debris removal missions, looking at concepts to remove large intact debris objects from low Earth orbit. And I'm now working primarily on my PhD research to use automation to aid early concept spacecraft design. I've worked on a couple different small bodies missions while in grad school. The first is billiards, which is a proposed demonstration mission of the billiard ball method of planetary defense, where if you have potentially hazardous asteroids to the Earth, you find a smaller near-Earth asteroid that crosses orbits with it, and then you redirect that small asteroid onto the collision course, using it as a kinetic impactor. I participated in the JPL Planetary Science Summer Seminar in 2017, where we developed a flyby mission of Chariklo, the largest star in the solar system. And I'm just now starting to work on a concept that I call a mission agnostic probe, where the goal is to try to develop a single spacecraft design that can accomplish a large number of small bodies missions. So you only have to basically sink the development cost once, and then you can mass produce this one spacecraft design with lots of objects for a greatly reduced cost. So for billiards, our mission concept was to find this small near-Earth asteroid crossing paths with a potentially hazardous asteroid. We call the small asteroid the alpha asteroid and the potentially hazardous asteroid the beta asteroid, and then launch a spacecraft to the alpha asteroid to first characterize it and then capture it, redirect it using solar electric propulsion onto a collision course with the beta asteroid. In the final hours before the collision, our spacecraft would separate into a instrumentation module, which contains all the high-power solar electric propulsion, as well as our primary science instrument, which stands off from a safe distance to observe the collision, and a terminal guidance module, which remains attached to the beta asteroid, or to the alpha asteroid, performing the final maneuvers to ensure that it is on a collision course with the target point on the beta asteroid. For this terminal guidance phase, we take the alpha asteroid and start it rotating such that the rotational axis is pointed from the alpha asteroid towards the beta asteroid. And then by rotating the asteroid like this allows us to having one thruster on the terminal guidance module pointed to the center of gravity of the alpha asteroid, perform a maneuver once every rotation to cancel out any radial deviation delta y from the target point on the beta asteroid. The next mission, like I said, is a proposed flyby mission of Chariklo, the largest star in the solar system. As part of the Planetary Science Summer Seminar at JPL, this was conducted in collaboration with the JPL's Team X, their concurrent design team, and it was designed to fit into the Frontier's mission requirements, launching in 2026 and flying by Chariklo. Science goals were to characterize the surface processes and characteristics, the surface chemistry and physical makeup of Chariklo, and look at complex systems that may be around Chariklo, that it has a number of rings, and it may have additional small bodies, and it may seasonally have an atmosphere, although it has not been expected at the time of the flyby. And then our third science objective was to characterize the internal structure of accomplished using 100 kilograms. So this is an overview of our science payload. It features visible and infrared imager and spectrometer, a UV spectrometer, a submillimeter radiometer, and a detector, as well as radio science using a high gain antenna. And this sort of science that I have observed is pretty standard for a lot of small bodies missions. The missions are customized to whatever the object is, but they're all very similar. That's where I started getting the idea that there may be an advantage to developing a single generalized spacecraft that can address a large number of missions without changing the design at all. And maybe something that can achieve 80% of the science at any one target for, I think, around a quarter of the cost, if not better. The idea is that there are lots of small bodies missions that we want to conduct. So for, in terms of planetary science missions, small bodies, for Discovery 13 and 14, there were 13 proposals that were presented at a previous meeting of this. The White House for Planetary Defense has released the National Near Earth Object Preparedness Strategy and Action Plan, which calls for developing strategies and spacecraft for rapid response characterization and potentially mitigation. And there's also interest in sending robotic missions as precursors for human exploration. So both Discovery 13 and 14 did select small bodies concepts. That's what's now Lucent and Psyche. But there are no, as far as I know, currently funded missions for planetary defense and funded missions for near Earth object exploration, precursor to human exploration. The thing with all of these different mission concepts is that they all have some goals that are unique to that mission type. So example for a planetary science mission as conducted by OSIRIS-REx. Essentially the mitigation operations for planetary defense and additional validation of trajectories and other elements for human mission and worksite preparation for potential astronaut missions. But the big first step where a lot of the science is accomplished for all of these is characterization. And the process and the spacecraft that you need to do that characterization is similar or identical as far as I can tell. Between all these different mission types, it's the target bodies that are different. But I think a single science payload can address all of these different mission types and replicate into an identical spacecraft all of these different types of bodies. Just as an example, I have a New Frontiers mission cost breakdown here. This is basically the cost breakdown for New Horizons, where the development cost is the large portion red, launch vehicle is gray, and it is important to note that the launch vehicle cost for New Horizons is somewhat more expensive than traditional all bodies mission. The Atlas 551, which was the largest launch vehicle of that type available. And then that really small blue cost at the top is the actual unit production cost for the spacecraft. So the idea is if you only have to pay that development cost once, and you produce a 4 or 5 or 10 spacecraft, you only have to pay that production cost and the launch vehicle cost over and over. So you can have a cost breakdown per mission that's more like this, for example, if you have 4 missions, sharing that development cost between each mission. So in order to proceed further with this concept, the first thing that I did is a prioritized list of which small bodies we would want. This is, the mission is not specific, or the spacecraft is not specific to a certain body. However, it still would be helpful to optimize the payloads, whatever the bodies of greatest interest may be. Having this will allow us to determine what the trajectories of those bodies may look like, which will help start constraining the overall spacecraft design. And will also help in determining what the science and measurement objectives may be in order to find what science payload is best compromised in those highest priority bodies. That will allow the design of the science payload, which combined with the overall spacecraft constraints will allow us to develop a notional spacecraft design that can then be mass-produced to conduct all of these missions. So just in conclusion, I think that this concept could allow something like 80% of the science per mission for a quarter of the cost. You can sort of think of it as the Model T of space probes, where it's not customized for any one mission, but it allows many people that would not be able to conduct small bodies that not be able to produce a much greater overall science. It is, so far it's been designed mostly for science missions, but the spacecraft addresses the planetary defense and human exploration as well. And it particularly, if you're mass producing these spacecraft and need a rapid response spacecraft with a hazardous asteroid, it's easy to take the next one that rolls off the assembly line and send that to a target of interest or potentially a scientific opportunity or things a new object that's discovered to reach it. And with that, I'll be happy to take questions.
I agree, Dan, from the University of Central Florida. I really agree with you that standardization is wonderful. The problem is this factors that mitigate it. This started in the 80s with nuclear diseases. And the problem is that each mission has enough unique requirements and a different enough environment that really what's costing you is engineering time and analysis to make sure that your replicated bus will actually do. And so I think it would be very difficult to achieve the savings that you're after. The other factor is PIs like to tinker. And engineers love to tinker with a standard design. And again, they will give you compelling reasons why X, Y, Z. And you're dealing with a aerospace company that's building the thing who has every economic incentive to keep doing that and bombarding you. So the way, I love the idea that the result has not been good over the last 40 years.
Lena Adams. Yeah. So, I had a question with the billiards concept. That was really cool. So, how much do you have to push an asteroid in order to do this? And what are the size constraints that you guys looked at for the size of the smaller asteroid that you have to move? Because you showed a really nice picture of rotating an asteroid, and the spacecraft was kind of big, and the pieces are kind of small. So, detecting that kind of asteroid is a little tough. Any thoughts?
Sure. So to start with the second question, the small asteroid we were looking at was on the order of 10 meters in diameter. That's probably around the maximum size you can have, and due to delta V, you need, I believe, was on the order of a centimeter per second for that initial the orbit change basically. And for the terminal guidance, I want to say it was either 8 centimeters per second, but I think it was 8 meters per second is the total delta V need for that. But that's actually an interesting area of future work, is to do more analysis on that terminal guidance phase. And that's something that we're definitely interested in doing in the future. As it turns out, half of the team that worked on that is sort of in the final months of completing all their PhDs right now, so it's on hold. But I think that is definitely something that's the big area of future work on
that. APL. So this is great. It's great to see. I think that some of the questions that you're looking at, as Dan said, have been kind of vexing us for a long time. And part of the challenge is going to be that the small bodies population is so varied that what people want to look at is a 100-meter potentially hazardous asteroid at 1 AU to, Oumuamua, to Ceres, whatever. One application is that you didn't mention is asteroid mining and companies that are looking to do that. And that might be an interesting possibility to look at whether those needs could be standardized in a way that an asteroid mining company might be able to say, here's our reasonably well-trained measurement needs. Have you thought about looking at that kind of application, or is that, like you said, you're close to finishing, you just want to not stand?
I'm definitely interested in continuing this after graduating. That's definitely something that would be worth looking into. I mean, I think it comes back to the fact that that science payload for the Chiricahua flyby mission, that's most science payloads for flyby missions, small bodies, look a lot like that. So you know, it may not be idealized. It will not be idealized for any one object that you're visiting, but you can sort of think of it as something between a primary mission and a secondary mission of a discovery class mission, something like that, where you can still have lots of meaningful science with a payload that was not originally designed specifically for that object. There's a
Also, just do you have any questions online? Or I'm taking that silence.
Okay, just a quick comment. It's very interesting work, and you mentioned earlier that there were no planetary defense interventions, but I think DART is a planetary defense intervention. So just to keep that. But this, I think this has a very interesting implications for subsets of different ranges from the sun.
Online question? Nope, okay. Over to Ken.
Static electricity. So thanks, Matt and Bryce. So we will now take a break of about 15 minutes, actually about 12 minutes.